Hello, we are Group 26. I am Srikantam Sai Venkat, roll number IMT 2023501.
And IMD 2023 118.
Hello everyone, my name is Aditya and my roll number is IMT 2023-114.
In this video, we present our Phase 2 submission, a multi-pipeline ETL and a reporting framework for web server log analytics. Our tool runs the same analytical workload over NASA HTTP web server logs from 1995 using 4 different execution backends: MongoDB, Python MapReduce, Apache Hive, and Apache Pig. Let me share my screen and walk you through the system. Here is the project structure. The entry point is main.py. The user selects one of the 4 pipelines at the command line itself. All 4 pipelines share the same parser, which is log parser.py, and the results are stored in same database, which is dbloader.py. Our dataset is NASA HTTP web server logs from July and August 1995, which has approximate tally of 3.5 million and also has 33 anonymous lines. Now, let me show you the structure of files which we use for our project. This is the structure. We have resource path, status code, HTTP method, all those stuff. We run 3 analytical queries on all the pipelines. Query 1 is daily traffic summary grouped by date and status code. And the query 2 is top 20 requested resources by request count. And the query 3 is hourly error rate for status codes 400 to 599. The same query, logic, and output schemas are preserved identically across all 4 pipelines.
Hello everyone, I'm Aditya and I implemented the MongoDB pipeline. MongoDB receives parsed records in batches of hundred thousands, performs in-memory aggregation using the group aggregation stage, and writes the results to PostgreSQL SQL. Let me run it now. The tool reads both NASA log files, parses each line using the share regex parser, and feeds records into MongoDB in batches. Batch IDs starts at 1 and increments sequentially. The runtime is measured from the first line read to last line PostgreSQL write, not including report rendering time. As you can see, it is the command is running now. So here, MongoDB finished in approximately 37 seconds, processing 3.46 million records across 35 batches of 100,000 each. It is the fastest pipeline because aggregation is native to MongoDB's documental model, and everything happens in memory.
Now let me explain that I implemented the MapReduce pipeline. This is a custom MapReduce Python MapReduce implementation. Pure Python map and reduce process running in process. This gives the MapReduce programming paradigm without cluster overhead for local execution. Let me run this command. Each batch goes through a map phase and emits a key value phase, followed by an in-memory shuffle sort, followed by a MapReduce phase that aggregates. For query 1, the map key is log date, status code. For query 2, the map key is resource path, and for query 3, map key is log date, log hour. Filtered to status codes from 400 to 599. Let's wait for the execution complete. Hmm. The MapReduce is completed in about 97 seconds, roughly 2.5 times slower than MongoDB. This overhead comes from the explicit map shuffle and reduce version, even though they run in the same Python rules. Thank you.
Okay, now let's see how Hive pipeline works. Let me run the command. Yeah. Now, Hive is running now. Unlike MongoDB and MapReduce, which ran entirely in Python memory, Hive processes data on HDFS using real yarn MapReduce jobs. Before our pipeline even starts querying, it uploads the past log records to HDFS as a structured file and Hive reads from there. The parsing still happens in Python. Only the aggregation and grouping logic runs inside Hive. We defined an external Hive table using regexd, a built-in Hive serializer that applies a serial expression to each row at a read time. This means the log format is handled entirely by Hive's schema layer, with no manual CSV or JSON conversion. The three queries Q1, Q2, Q3 are written as HiveQL, which is essentially SQL when we execute them through beeline. Hive Server 2 compiles each query into a MapReduce job and submits it to Yarn. You will see these separate job submission in the output, one per query. Let's wait for that. The Hive pipeline might run between 150 seconds to 196 seconds, and as it is using real yarn scaling. But if we use to run the Hive pipeline using the memory of a laptop itself, it might take less time, like 80 to 90 seconds. The scheduled time adds extra weightage to each yarn MapReduce job goes through a full scheduling cycle. The resource manager allocates container, the node manager launches the JVM mapper, scans the HDFS blocks, and the reducer aggregates the output. On a single node pseudo distributed cluster like ours, the container startup adds roughly around 40 to 60 seconds of overhead per job, even before any data is touched. That is why Hive takes nearly 150 to 190 seconds for data, whereas the MongoDB takes nearly 137 seconds. The query logic itself is fast. It is the yarn scheduling overhead that dominates. One important thing we verified is that Hive is genuinely running on yarn and not in a local mode. The mapred site.xml configuration has MapReduce framework name set to yarn system wide. This applies to both Hive and Pig. Both submit a real yarn scaling, and it you can confirm this by running yarn application list in another terminal while Hive is active and seeing the application registered with the resource manager. Yeah. Okay, now let me show you the Pig pipeline. Let me run this command. Yeah. As you can see, the records are getting uploaded into HDFS. Actually, the peak might take nearly 17 minutes to complete on a single node yarn cluster. We might not show you the whole 17-minute process, but we will just show you how it works, and we'll also show you the whether we are using yarn cluster or not in another terminal by using yarn list application. Now, let's wait till the records are getting uploaded. Now, yeah, as you can see, the job is getting run on the terminal. Let me go through the under terminal. See, as we can see here, we can see that the yarn application is getting run and the pig application is also getting run. So we can say that we are using a real yarn cluster. So now let me also take you through the code as well. So this is the pig pipeline.py code. Pig writing is a data flow language. Instead of writing SQL, you describe your data as a sequence of named relation, and Pig compiles that into one or more MapReduce jobs behind the scenes. Our pipeline has three anchor queries. Q1 groups by date and status code to get daily traffic counts. Q2 ranks the top 20 most requested resources. And Q3 computes hourly mistake rates, what fraction of request per hour returns 4 or 5 as a status codes. Each query each query is a separate store operation, which means Pig submits three MapReduce jobs to Yarn, one per query. That's why the total runtime is long. Three full MR circuits, each doing a sort and shuffle over 3.4 million records is a bit huge. Now, one of the more interesting engineering decisions in this pipeline was how to handle the log parsing. Our input is Apache combined log format range, like host names, timestamps, HTTP method, bytes, and all of those stuff. Pig does not have a built-in SERD for that format the way Hive does. Like it does not have an inbuilt parser to do those stuff. Our first attempt was a Python streaming UDF, a custom function you register with pig that processes each line. But on Java 17 and pig 0.17, streaming UDF paths has a known NPE bug in the Python executor. The JVM initializes a null process, handles and crashes before it ever reads a record. Our fix was pre-parse the TSV approach. The pipeline runs the method in the pipeline in the Python parses the NASA log lines first using the same regex parser we share across all four pipelines. And then we write each batch as a clean tab separated file. Uploads that to HDFS and the pig reads pure TSV with pig storage. No custom UDF needed. The parsing is identical to what MongoDB and MapReduce use. Now, as we have seen that we are using yarn confirmation and notice that, let me show the reason it takes 17 minutes while the Hive took about 2.5 minutes for the same data is parallelism configuration. Pig on a single node setup defaults to a low reducer account, and each of the three queries has to fully sort 3.4 million records. In a production cluster with 10 nodes, this would complete in 2 minutes, but in a single node system, it is taking nearly 17 minutes. When pig finishes all three store operations, our pipeline reads output files from HDFS. Pig writes the results as a TSV files in the output directory, parses them, and calls the same dbloader.save Q1 and Q2 and Q3 functions that every other pipeline uses. That's the key design point. All four pipelines, MongoDB, MapReduce, Hive, and Pig, write identical result schemas into PostgreSQL, our report.py. Our report.py script can then do a direct cross-pipeline comparison, same Q1 row count, same Q2 ranking, same Q3 mistake rates. The numbers are identical because they all are parsed using same files, using same regex parser. Once pick completes, you will see the runtime printed as around 17 minutes or nearly 15 minutes. Yeah, so that's our pick pipeline on a whole. Now let me
Start.
show you the results for all four pipelines. Let me run this command. Yeah, here we can see the results for all different batch sizes and average batch size and the runtime issues. Yeah. We can see MongoDB is the fastest among all of them. This is a comparison view. It pulls the most recent run for each pipeline from ETL run tables. Look at the runtime column. Now my friend Revant will explain the runtime differences. What might be the reason for it?
Now let's see the runtime difference. These differences aren't random. Each number reflects the overhead model of each engine. MapReduce takes 93 seconds due to explicit map shuffle and reduce phases running in the pure Python across 35 batches. MongoDB is fastest at 37 seconds because aggregation is native to its document model. No JVM, no continuous scheduling. The data is already in the memory after insertion. Pig is slowest at 1032 seconds because it submits approximately 5 yarn map reduce jobs and each carries 60 to 120 seconds of container. Startup overhead on each on single node cluster. Resource manager scheduling, node manager JVM launch, task execution, teardown. 5 jobs, 5 jobs times 3 to 4 minutes. Each gives you 70 minutes. On a 10 node cluster, these jobs run in a parallel and pig would it would be among the fastest. Now my friend Aitya will explain the implementation complexity and correctness.
Here, in terms of implementation complexity, MongoDB was the simplest. Its aggregation pipeline was maps directly to SQL groups by semantics. So the query logic is expressive and concise. Hive was clean and declarative. Once the schema was set up, regexRD handles raw log parsing inside Hive itself. Required the most custom code. Since we implemented the map shuffle reduce logic from scratch, after Mr. Job became incompatible with Python. 3.14 Pig has the steepest setup challenge due to yarn configuration. Java version conflicts and the streaming UDF crashes on Java 17. Now the most important is scroll down to Q1.
Yeah. So now, as we can see, we can prove the equivalence as well. The system is completely correct because for each and every query, for different pipelines, the number of records which are written from the pipelines are same. So we can say that our pipeline is working absolutely fine. And the number of malinformed are 33, which are like 0.01 parse failure rate and is identical by all four pipelines. Now, my friend Revant will close the whole thing.
Now let's come to the conclusion. System demonstrate the fundamentally different processing paradigms. Document store, Python map reduce, SQL on Hadoop, and Dataflow can be made interchangeable at the time interface level. Each pipeline writes the name to the same as post-technical scheme, and report layer sees no difference between a MongoDB run and a Pig run. That concludes the live demonstration, and thank you.
Yeah, thank you all.